thanks, Hongyi, for having the talks so early in the US.
It's my pleasure.
You can start share screen.
Sure, yeah, let's do that. Can you see my screen, by the way?
Yeah.
Oh yeah, I can see. I can also see my screen on the on the meeting room. All right, let's get started. Yeah, thanks. Thank you so much for organizing such a great event, and thanks a lot for having me. Today I will basically talk about when will gradient compression be useful in distributed training systems. The title may look like a bit surprising, but hopefully when we dive right in, you will find it more reasonable. This is a joint effort with an amazing group of folks from both academia and industry. And today I will basically talk about kind of like just the 4 points of like what is gradient compression basically, and why we need them, and when will gradient compression be useful in real distributed systems when we deploy them in a real cluster, and how to design basically useful gradient compression for the future applications. So basically, what is gradient compression? So gradient compression is something like this talk will basically focus on data parallel distributed training, and in data parallel distributed training, so the message is that communicated across distributed nodes actually gradients. So each of the nodes just basically partitions the input, let's say data batch, and the grid is a gradient, and kind of like a synchronize that across the entire cluster. So when the model becomes large, as we can imagine, the communication can actually become a bottleneck. So gradient compression is a technique that actually deployed to kind of like seek to tackle that communication overhead issue. So if we think about that, if our size of the gradient is kind of like a vector, then the amount of communication is that for each of the elements, we have to communicate like a 32-bit like floating number. So what we can do is that we can sometimes reduce the precision of each of the like element, say from 32 bits to like, let's say 2 or 4 or 8 bits. Or sometimes we can kind of sample the gradient elements such that we do not communicate over all of the gradient elements. Instead, we just sample k important one, or randomly sample k like gradient elements among the entire gradient elements that are computed by each of the worker node. So basically, why we need the gradient compression? So measured by it has been widely observed in the past literature that if we actually just use like large distributed cluster, and we are trying to train large model. So say in this example, it's coming out of SOSP 2019 paper that so the x-axis here is basically the number of GPUs in the cluster, and the y-axis is measured communication overhead measured by the percentage of the communication that take into the like of the entire iteration. So the percentage of the total time of communication over the entire iteration time. So you can see as the cluster size grows to like 32, something as large as 32, the communication can take almost like 80 or 90% of the entire training time. So that basically means the communication can be actually an overhead in like even in data parallel distributed training. So so we want to basically ask the question. So this sounds a little bit surprising, but if you look into the literature, that most of the gradient compression are benchmarked by either the authors come up with their own implementation, or they just come up with some like a toy implementation. They just write down kind of like a training pipeline, and then after the training, they basically handle the communication by themselves. So we are basically asking the question: what if we just take the method and really try to implement them into what people are using? Let's say PyTorch or TensorFlow, the API they provide to conduct distributed training, and deploy into some cluster, let's say offered by public cloud, let's say like AWS. What will actually happen? So it turns out we're basically just implementing this each of the kind of like gradient compression method we can find. Those are state of the art. we're trying to optimize them very well, or kind of finding the state-of-the-art implementation, and really implement them in like in the real distributed system on the like popular benchmark. So here we can see that we are basically choosing 3 state-of-the-art gradient compression method, specifically power SGD, top K, and the sign SGD. So the dark blue bar here, we call system optimized SGD, is basically PyTorch DDP. So that's just the API, and we just take the like cluster instances from the EC2, which from AWS. So those are the kind of like standard setting we can possibly find. And surprisingly, we observe that it seems the PyTorch DDP always wins in the most of the scenario we tried. So clearly, gradient compression does not work quite well in practice. That basically seems to give us the message. So we want to ask why. Why don't we see significant speedups even like in the practical scenario? So here are a few reasons I want to share. So first reason is basically so when we consider the basically computation graph of neural network training. So sometimes we basically have to compute the backward propagation, and then we have to synchronize the gradient. But however, those operations does not necessarily need to be serial. They can be actually overlapped. So once we compute the gradient of the last layer, we can immediately start the communication of the gradient of that layer. So if we conduct, turns out in practice, like people like the overlap basically are implemented into the API, say PyTorch DDP. So if we basically just conduct that, the communication overhead is largely reduced, such that the space for gradient compression to work on become much smaller. And also, the batch size also kind of like take into play into this like scenario is basically if we use a larger batch size, so computation scales with the batch size, but communication has only to do with the model size. So basically, if we use a larger batch size, the communication overhead becomes even smaller. So that's the first reason. The second reason is basically sometimes a gradient compression can be actually computationally heavy. So so in this example, the backward propagation only takes like over 120 milliseconds, but sometimes the gradient compression can take even longer, or kind of like at least comparable to backward propagation. So the overhead of the encoding and decoding, so basically computing the compressed gradient, can be as heavy as the backward propagation. And also sometimes the gradient compression is not compatible to the all-reduced API. So which basically means they have to only be implemented into a kind of like a less efficient gather API, such that their performance won't be basically comparable to the all-reduced collective communication API. So with that, can we actually build a cost model to capture this in practice? So basically, if we consider the common strategy that's basically called a bucketing strategy, that we are kind of like splitting the gradient into a few buckets based on their size. We can basically cut or aggregate the gradient, and we can actually build the cost models in this kind of like a format. Basically, we're trying to capture the first term is basically how the computation can be overlapped with the communication of the first k-1 buckets. And then we can also capture the communication of the last bucket. So it seems to be a straightforward communication model. And then we can also plug in the gradient compression here is basically new communication cost plus the encoding and decoding cost. So it seems this cost model captures the communication very accurately, at least even with this simple cost model. In kind of like most of the task we tried to experiment in our work. So why this cost model is useful is basically given the implementation and then the cluster and also ML model, and given the bandwidth available in the distributed cluster, we can basically predict what's the compression ratio we actually need to achieve linear scalability. So basically, for instance, this is a quite standard bandwidth we can observe in a distributed cluster. It's basically if we get like 10 Gbps bandwidth, we don't actually need such kind of like a massive compression ratio. So sometimes it seems like just a 3 or 4 like times compression ratio will be good enough. So basically, like to summarize, basically, I want to ask how to design the next generation of gradient compression to make them become really useful in practice. So basically, we should focus more on the encoding and decoding cost, as we just showed. So the compression ratio can be important, but not as important as the encoding and decoding cost. And we should also make sure the compression method should be compatible so or reduce API. And basically, we should also focus on the good put. So the gradient compression method should not just crush the model's accuracy. So let's let me walk you through one example, like how a gradient compression method can be useful and how can we actually design a concrete gradient compression instance. So basically, previously people have looked into like gradient factorization. So basically, use the low rank factorization of the gradient. However, the factorization can sometimes become expensive. So in kind of like this concrete example, we want to ask, what if we just incorporate the compression into the training itself? So instead of like factorizing gradient of those 3 layers example, neural network example, so we can just factorize the model weights instead of the gradients like explicitly. So basically, we just train the like low rank network instead of like factorizing their gradient. And since the network size is reduced, the gradient is also basically become smaller. So however, the good put there is bad, right? Like if you just train the low rank network, sometimes it's not initialized very well, or the capacity of the network is not good enough. So we can see the large accuracy gap here. So how can we improve that? Is basically we can look at the network's model weights, and we can find like some of the weights are kind of like inherently higher rank, so that's not quite tolerable to low rank factorization. And some other layers can be actually low rank. So we can basically detect them to decide which layers are easier to factorize. And also, it turns out that directly start from low rank network is not quite desirable. So we can basically start from kind of like a warm up the origin network a little bit, and gradually make them become low rank. So we basically warm up them for a few epochs and factorize them, and basically then start to train the low rank network. And turns out those 2 simple heuristics fix the good put very well. So now you can see that with incorporating those 2 techniques, the good puts become much better. And since we are using this method, we do not have any encoding and decoding costs. And sometimes the computation can also becomes faster because we are training a smaller network. And overall, it becomes like the end-to-end communication time can be much better compared to the like even the state-of-the-art like a gradient compression method and also the PyTorch DDP method here. So one thing we can see in the like previous work, the factorization, is that we have to basically detect the factorization basically ratio, the rank we want to use for each of the layer. So how can we make them basically automatic? So it turns out we can use some of the metrics, let's say rank estimation of each matrix layer. So basically each layer's parameter weights to basically detect the rank we actually want to use in practice. And sometimes the warm-up, the number of warm-up epochs can also be important. So here we observe that actually the estimated rank becomes stable in the end of the training. And we can also use that to determine what's the rank we want to use to factorize each layer. And turns out the thing becomes kind of like very interesting is that the rank can actually be solved like explicitly if we don't care about the training speed. So here's the work like from CVPR last year. It's called like LC compression. So which is basically the orange line here. And turns out our heuristic can basically use the rank estimation, can basically be get the results that very close that match very closely to the explicitly optimized rank selection. So basically that means our method captures the rank, the basically true rank we want to use for each of the layer very well. And turns out if we basically adopt the automatic version, we can kind of like compress the network even further to achieve even better compression ratio. So with that, I want to also share a few open problems. So basically, the first is I kind of like only captures the data parallelism in this like talk. So how can we also do like message computing in beyond data parallelism? What will happen in model and the pipeline parallelism? And also, how can we make the entire? So we have the cost model. Can we use the cost model to determine the optimal compression ratio during training? And for each of the given tasks on each of the given cluster. And also, it seems the entire thing, the message computing, is not quite integrated quite well in the current software stack. So can we actually build one that with high performance and optimal implementation? So with that, that's all I have to share for today. And I'm ready to take some questions if there are any.
I can ask a question. So, closer.
That'd be wonderful, so everyone can see the person asking questions.
Okay, hi Hongyi. Thanks for the great talk. So I had one question, which is, if I'm not mistaken, when you implemented Power CD and the other gradient compression, you were expressing them with a PyTorch API. So presumably this gets run in the GPU, but it can have quite a little bit of overhead. And some work, or which is maybe parallel to your own, last year in SOSP, the high press paper had implemented several of these compressors directly using CUDA kernels, because they were saying, otherwise it's very high overhead to begin with. So I was wondering, what was your thinking when you were trying to do the work, and why did you not go down to the level of CUDA to minimize the overheads here?
Oh yeah, I think that's a good question. That's actually a common kind of challenge we basically received in this work. So basically, how can you make sure your like implementation is optimal? So I think that's very hard to that's actually very hard to have a kind of like a guaranteed answer that once we say this implementation is optimal, this other day you can also basically try to use better optimization technique. Let's say, like the example you mentioned, you delve into the kernel implementation level, you find the better implementation. So that's actually something like but the point I want to make here is basically our cost model can still capture that actually. Like for the encoding cost you give me, I can still predict that like how does the method perform. So that's the main message here. It's not going to criticize the previous method. It's just to say, like, how can we capture, can we characterize or find the representation of different like gradient compression method, and when can them actually becomes useful. So like as in the example you mentioned, like if we really implement, let's say Power CD or whatever method in the down to the CUDA level. So in our cost model, basically the communication can be still very efficient. But if we take into the encoding and decoding cost, it can be much cheaper. So that basically means that the method can actually be useful. So like the point we want to make is basically if you take the existing like implementation, right? Like we just take the implementation in the Power CD paper. We also implement that actually the PyTorch system implementation in the original PyTorch version, because that's integrated in the gradient hook in PyTorch. So it seems to be compatible with our like observation. But yeah, that does not disagree with your observation, right? Like if you really push down to the bottom level, I believe that can be that can work well. So that's also related to my open problem here. If we actually find a way to basically kind of like come up with a high performance implementation in the library, I believe we can actually make you know, a gradient compression be adopted more kind of like widely in the industry level like platforms or kind of like products.
Thank you.
Yeah, thank you so much for the great question.
Okay, thank you, Hongyi. So thank you for joining us so early there. So we are going to move on to the next talk by Janelle. Hongyi, you're welcome to stay and let's do the talk.